Howdy, howdy, this is Mr. Potter. In our previous lesson, we talked about the idea of dynamic allocation, the idea that I could take some data structure and rather than having to set up some initial data structure with a fixed size, like an array, what we do is we set up data as we need it. So if I only need one node, one piece of data in here, I'm only going to have one of these. If I need three, well then I create a second, I create a third, and I make sure that they're linked in some way so that I have my three pieces of data. And we talked about how we would create such a linked list of objects. What we can do though is we can take this concept of linking dynamically and apply it to some of the data structures we've talked about so far. So the first one I want to talk about today is the idea of a dynamically linked stack. Now keep in mind what we had done before is we had set up an array of a fixed size. We had a pointer to head, we had a pointer to tail, data was put in here, we put in new data by moving tail over and putting stuff in the array. And then what we would do is we would pop the elements out, basically taking the 6 out and pointing tail to here. And so what would happen is the data would be taken out of the stack. Technically though, this array still contains a 3, a 1, a 7, a 5, and it still contains a 6 until we push some new value over. This data here is still being used even if I pop all the way back to having just one element in my stack. For comparison purposes, what would happen is I would have a head and a tail. I would create a node that contains a 3, and then if I wanted to push a 1 onto the stack, then I would create a new node, put a 1 in here, and then make sure that this node linked to the previous node. And then of course I would create a new node with this 7, I'd create a new node with the 5, I'd create a new node with the 6, and this node right here, my tail, would have to be pushing to this. Here's where my head was. This is how I'd know if I was empty, as if my head was null. But if I want to pop, then all I'm going to do is basically get this data out and get rid of this element. So this is now pointing to null. I'm not going to have a pointer at this point. So the idea behind this is that as I pop elements off of my stack, then my stack is going to take up less and less memory. If I add more elements, then my stack is going to take up more and more memory, but I'm only going to take up as much memory as I physically need to. Now there is one thing that we kind of need to discuss, and that's the idea of reclaiming that memory. So if I have a stack and I want to pop this 5, well, I want to get the data out. So, okay, fine. Here's the 5, and I do with whatever I want to. It's stored as an integer. And then I'm going to set this pointing to null, so this chain that connects it really doesn't exist anymore. But I still have this memory object out here. So what I need to do is I need to tell the computer to delete this pointer. And so the delete command is a command that tells the computer this piece of memory that I'm pointing to is no longer needed by myself. And so you're free to give that back to the operating system. And so the idea of deleting a pointer when we don't need it, because we're now telling the computer to get memory as we need it, we do need to do the sensible thing and release that memory back to the computer if we don't need it anymore. Now, some computer languages have an issue with this. They don't do this automatically. Java, if you remember, does have a garbage collection, so it does this, but it does this at intervals. And if you don't do this, then you can create what's called leaky code. You can have memory leaks. And if you have too many memory leaks, the computer allocates this memory and then doesn't know that it's not being used. The computer can eventually run out of memory. So it is something to be aware of. So we're going to talk about how to implement our linked list. So I'm going to open up a file just like we had before. So I'm going to open up node, and this is the node that we were talking about last time. So notice that I've got the template with class T, I've got a struct node, and it has 2 elements to it. It has a t variable for data, that t component, and then it's got a pointer which points to the next node in our list. So what we're going to do is we're going to create a file called linked stack. So here's linked stack.h. And what we're going to do is create the idea behind our stack. Now our stack is going to look exactly the same to whoever's programming, because I'm going to have the same functions. I'm going to have push, I'm going to have peek, I'm going to have pop, I'm going to have an isEmpty. What's going to be different is the structure behind it. So I want to make sure that I include node.cpp, and then I want to define stack underscore h, just like I did before. Template stack t, it's not stack t, class t. And then this is going to be my class stack. Now, the first part, the public part, is going to look very similar to what we had before. I'm going to have a void push with a t item. I'm going to have a t pop. I'm going to have a t peek. And I'm going to have a bool isEmpty. Because to the public, this looks exactly the same as every other stack. What's going to be different is in private, I'm going to have a node of type T called head. And I'm going to start it off to be null. And that's it. That's all that we really need here. And then once I've done this, I want to include linked stack.cpp. So that's my linked stack.h. Notice that it actually looks a lot simpler than the linked stack.h that we had before for our array. So I'm going to create one more file. This is going to be the meat and potatoes. No, I don't want a terminal. I want a file. This is going to be linked stack.cpp. So now what we're going to do is include IOStream, and we're going to include std accept. Remember that we need both of these in order to throw the exceptions that we're going to throw if we're trying to peek or if we're trying to pop from an empty stack. And of course, if not defined stack underscore h, then we want to include linked stack.h. So now we're ready for the actual code using namespace std to make sure that I can use my throw my exceptions as I need them. So template class t, we're going to have our bool stack of t is empty. And I am empty if head is equal to null. If head is equal to null, then I'm empty. If head is equal to a node, then that node is going to contain all of my data. So I just want to return the result of that if statement. And that's my isEmpty. A lot easier because we only have one pointer instead of two integer variables. So now we're going to have template class t. This is going to be our t stack peek. Remember, this is our non-destructive one. So all I want to do is I want to get whatever is in my data. So I'm going to say if head is equal to null, in other words, if I'm empty, then I want to throw a standard exception out of range. And I'm going to say attempt to peek with empty stack. And if I get out of this statement alive, then what I want to do is I want to return head pointer data. So head arrow data is what I'm going to be returning here. Remember, this is the non-destructive one, so I don't have to get rid of that node. That node is still part of my file. So now let's talk about what pop would look like. So template class T, and we're going to have T stack template T : pop. Now this one's going to be destructive, but I'm still going to have that if head equals null, then throw standard out of range. I'm going to say that we are going to attempt to peek with empty stack. If I make it past this point, then I know that my stack is good, so I need to get a couple of things. Number one, I need to get my data. So my output is going to be whatever head arrow data is. And then I'm going to say node type T pointer old node is going to get whatever head is. And then I'm going to redefine head. Head is going to get head arrow next. And then what I can do is, now that I've kept track of this, now head is pointing to the next element in my stack. All I need to do is delete old node and then return output. So let me draw what's actually happening here. So let me go to my thing here I want to draw. So I'm going to be adding an element. So here's the first element. I'll call that a 3. Okay, and head is pointing to that. When I want to create a new entry, I'm going to create a new node, have it point to whatever head's pointing to, put the data in here, and then say, head, you're now pointing here. And then if I want to create a new entry in here, then I'm going to create the node. I'm going to have its next point to whatever head's pointing to, put my piece of data in, and then say, no head, you are now pointing here. So now if I want to peek, I just ask head, what's its data? So it would tell me the 5. If I want to pop, then I'm going to say, okay, I need to keep track of this node. This is my old node. I want to keep track of the data. The data is 5. This is my output. And then I want to say head, you're going to point to whatever head.next is. So head is now going to point to this. And then I delete old node, which gets rid of this memory location entirely. So now head points to 4, 4 points to 3. Output is 5, and this is stored in a variable that's going to be returned. So that's actually what's happening here in the structure of this node. All right. So then the last thing that we really need to do is take care of our push. So we're going to do template class T, and we're going to do void stack template T : push with the T item. And this is going to be the item that we're going to put on the stack. So the first thing I want to do is I want to create a node. So node of type T, and it's going to be a pointer called in, gets new node sap T. And then I'm going to say in pointer data is going to get whatever item is. I'm going to say that in pointer next is going to be head, and then head is going to point to in. And so that's what we were talking about just a few minutes ago. If I already have a stack that's pointing to possibly other nodes, and this is where head is, then I'm going to create a new node. I'm going to put my data in there. I'm going to make sure that next points to whatever head's pointing to. And then I move head over. So now head is pointing over here. And so head points to 6, 6 points to 5, 5 points to everything else. All right, so now that we've finished the code, let's go ahead and save this. And then we're going to try and compile it. So let's go ahead and do that. G++ linked stack.h stack.h. Couple of issues. Notice it says that I don't have a semicolon there for the null, which I need to take care of. It also says null is not defined. So let's go ahead and go there. Let's take care of the semicolon. And what we'll also do is take care of our undefined. So if not defined null, not quotes, null, then we'll go ahead and define null to be 0. Okay, so now let's try running that again, see what happens. Okay. Oh, and I probably shouldn't have this, probably need a constructor, don't I? So I don't want to have null here. What I want is I want a constructor. So let's go ahead and do stack type T. And then we'll just say head gets null here. And really, did I misalign all of those? My goodness. All right, so let's save that. Let's recompile, and that looks good. Now, so what's nice about this linked stack, the way that we've written, because we have the same function names and the same function parameters, I can go into a function like calculator, and I can change it from array stack to linked stack. And if I save that, and I want to compile my calc main, then I should have no problems. Now notice I'm getting an issue here. It says struct node has no member in on line 42. So let's take a look at line 42 real quick. Okay, so we declared in here. Then we said in, oh, I need to say head equals in. That's right, that should be an assignment. All right, so let's try that again. That looks good. So if I run calc main, then notice I'm getting the same results from the calculations as we were expected. Let me go ahead and open that file real quick and make it a side-by-side type thing. So remember, our first expression was 3 plus 4, which is 7, plus 5, which gives us the 12 that we get over here. Then we have the 3 times 4, which is 12, plus 5, which gives us the 17. Then we have the 3 plus, and then 4 times 5 is 20, so that gives us 23. And then we have the 3 plus 4 in parentheses, which is 7, times 5, which gives us 35. So we get the same output that we're expecting, just we're using our memory a little bit more effectively. Now I can do the same thing with stack sort. So if I take stack sort and just change it to linked stack.h and save it, then we'll go ahead and compile that, stack sort.cpp. And we'll go ahead and do output to stack sort.exe. Then I should be able to run stack sort, and I should be getting the same output. Let me go ahead and flip this over here as well. So remember what we had did in our stack sort is we tried to sort this array here, this 1, 2, 3, 4, 3, 2, 1. Let me go ahead and uncomment this instead. So now we're having the numbers from 1 through 9. So let's recompile and rerun. And notice that it puts those numbers in order. What's really nice about this idea of a linked stack is that it allows us to dynamically allocate our memory. So we're not working with a fixed array. We don't have to copy the elements of that array to a larger array later on. Instead, we take care of the memory as we need it, including getting rid of old memory that we don't need using this delete command. So once again, this is Mr. Potter. Thank you for watching. Have a great day.